Okay, welcome. Today I am going to discuss how to orthorectify historical aerial imagery that are collected with these frame cameras that have fiducial marks using Agisoft. Now, today we're not going to talk about doing this with the most accuracy possible. What we're trying to do this with is speed. And one of the reasons for that is we already have some imagery of this area around this time. And it's pretty good. We're happy with it, and so duplicating that is not really necessary. But the other reason is that this was collected in a single track. It wasn't collected with side-by-side flights, so we couldn't get a good product out of this if we wanted to. But we can get an okay stitched together ortho of this area using these images, and these ones are important to us because these ones in particular were collected in 1975 just after a big storm hit the community, and it's really important that we look at what the community was like at that time in order to know more about the impacts of that storm, like finding a debris line. These photos appear to have been collected with the intent of doing a really high-res survey of what the community looked like at that time. And you can see, I'll zoom in on the one photo here, these are really high resolution. This is 1975, and you can see, I mean, you could measure the diameter of individual barrels that are out there and logs, and you can count the rungs and boats, things like that. So you can really see a lot of detail, and this will tell us a lot of information about what the community was like at the time and how much it's changed. So it's really good information to have. We don't want to lose it. It's certainly the highest resolution data that we've ever seen for these areas this far back in time. So we want to have it in a mapped format where we can use it for comparison. But like I said, the data wasn't really collected perfectly, so we're not expecting to get a perfect product out of it. So we're just going to run through this quickly, and I'll show you how to do that. So to get started, you load in your images and then go to Tools and Camera Calibration, and you'll want to fill in the focal length, which you get from Earth Explorer in the metadata, and then you'll want to check on Film Camera with Fiducial Marks, and that just tells the program that it is a camera that has these little X's on the corners. So then the next step is to identify the location of your fiducial marks. And I'll just go to my first image here, and in this I've already identified them, so you can see 1, 2, 3, and 4. But to do that, to start placing them, just zoom in to the top left X, start on the top left, and you'll want to right click and go to Place Fiducial, and then select New Fiducial, and that will just automatically generate number 1 for you. And then you can press page down, and that'll go to the next image, and it'll be zoomed in at the same area around that X. And so now you can right click, and when you go to place fiducial, 1 will show up on your drop down list. So I'll just click 1 and put it there, and I'm going to page back up and place my number 1 here again. So you can page through and just try to do your best to place them in the center of that circle, and do that for all of number 1, and then move on to number 2. Number 2 is at the bottom right, so remember we started at the top left, 2 is at the bottom right on the opposite side, and then when you finish that, go to 3, which is the top right, and then 4, bottom left. So once you've placed them on every single photo, we can move to the next step. So what you want to do now is tell the program how large this image actually is. So we can go back to camera calibration, and now we can go to this tab called fiducials, and we can enter the coordinates. So the way this works is basically not very intuitive. The image center is given an origin of 0, 0, and the location of the fiducials are measured from the center, and they're measured in millimeters. So we learned from Earth Explorer that the size of this image was 229 millimeters, and it's square, so 229 by 229. So the way that things are measured is using an x and y axis, but x goes from top to bottom and y goes from left to right. And the top is a negative x value and the bottom is a positive x. And the left is a negative y and the right is a positive y. So that means that the number 1, our first fiducial, is placed, it's at the top, so a negative x direction and a negative y direction. And you also notice that it is half, the values that I've added here are half of the distance, so half of the width of the image itself, which was 229. So I enter in minus 114.5 millimeters for x and y. 2 is the opposite corner, and so it'll have the opposite signs but the same distance, so positive 114.5. 3 is in the negative x direction but positive y, and 4 is in positive x and negative y. So fill out your fiducial coordinates, and that will tell the program a lot of information about the camera lens. There is this pixel size, which we're not going to fill in. This is a measurement of the actual size of the physical pixels on the camera sensor, and so it would be a very small number, like 0.02 millimeters. But the program should be able to calculate that now because it knows how many pixels are between these fiducial marks, and then it knows the distance between the fiducial marks now. So it should be all good. And that's just going to help the program in the long run really put these images together and get a good lens distortion. And because when these are scanned, they're physically printed out images and then scanned on a scanner, and they kind of jumble around as they scan, and they did their best to kind of keep them center and straight, but the fact is that they move around a little bit, and so the camera center moves and it starts to cause issues in the lens correction and other things down the road. So this resolves that as best we can, and we'll press OK. We are happy with our coordinates, and let's see. Now, one other thing I want to do is mask. So there's a couple reasons I want to mask this image. One is I don't want this black boundary because this will actually show up in our ortho and it's ugly. And 2 is sometimes the writing on the images causes problems. The program will actually match up the letters and project them really far away from the image, and it can just distract the program and possibly cause issues with your map. So to mask, you can click the rectangle selection tool, and I'll just click the top left fiducial and drag this rectangle to the bottom right fiducial, and then invert. So right now I've selected basically the entire image, and I'm going to invert this selection using Control-Shift-I. Control-Shift-I inverts our selection, so now you can see a red boundary that goes around the entire image as well. And then Control-Shift-A will add our selection to the mask. So Control-Shift-A adds the selection to the mask, and there you go. So one thing you could do is just use the steps to save your mask and then import to all images, but I only had 10, so I just do this for every one. So again, we'll do this here, drag down, Control-Shift-I, Control-Shift-A. So once you have a mask for every image, we can move on to our alignment. I'm going to go to Workflow and Align Photos. I had already run one in this project, so I'm going to hit Reset Current Alignment. And these are the key points and tie points I used. It's probably overkill, but that's seemed to work for me. And I'm going to check on Guided Image Matching, and this apparently will assist the program with dealing with images that have a really high megapixel. So these images are about 50 megapixels, and so this button is specifically for them. Press OK. Alright, we've built our sparse cloud, and here is what mine looks like. It's a black and white image, so it's just salt and pepper. There's also this big bounding box around it. Came out really flat. Looks really nice. So normally we might do gradual selection or do some cleanup, but I am just going to move on because, again, we want to do this quick. We just want to move on with our lives, and there's no glaring points that should probably be removed. If you have points that are obviously causing issues, or you see different levels of your planes, then you might have to troubleshoot that. And if it's just an entire mess, you might ask someone for help, or maybe just scrap it. Maybe the image collection was so poor that it's just not possible to get a good product out of it. I'm going to click on this camera to show cameras, just to show this is where the program figured out the cameras were and the way that they're facing, so you can see they're flying along and just in a single line taking pictures. And so again, there's no side lap, which is why this data set, we don't expect to get a perfect product from it. But like I said, we still want to use it, so we're still processing it, but I don't expect the best thing to come out of this. And notice I didn't put any camera coordinates in here. I didn't put the estimated coordinates from Earth Explorer or the flight height, because those values aren't very good and they can sometimes actually throw off the program. So I'm just going to let the program deal with it itself, and let the program decide what's best, rather than putting in some wonky values that might cause things to get worse instead of better. So I'm going to save here, and I'll press optimize cameras, so this little magic wand, and it sort of says, okay, all you really need to do is fit F and then K1 and 2, which makes sense because these are really highly calibrated frame lens cameras, so there shouldn't need to be a lot of alignment adjustments for it. But I still just like to click adaptive and let the program be smarter than me. It took no time at all because there's not a lot of points and there's not a lot of fixes to be made, and nothing really changed, so that's good. So now we can go to build our dense cloud, and again you'll want to save here. There's a step in the dense cloud that you might find out the hard way, that you need to change a setting or else your computer might crash. And it automatically put depth filtering as mild. I usually run as aggressive, so I'm going to keep there. Quality high. I'm not going to calculate point colors. It takes a little more time and it's black and white, so I don't really care. And just press OK. We have created our dense cloud, and since I didn't do point colors, it looks a little purple. I can center click to pan up and bring it to the center of my sphere. And here it is. This is Hooper Bay. You can see some topography here. A lot of holes where the buildings are, but that's okay. Those will get filled in a second. But yeah, looks pretty good. It's a hillside, it's a tank farm, the road is raised a bit, so it's like it worked pretty well. If you zoom in more, you can kind of see these concentric circles radiating out from the center line of the images collected, and that is an indication that there's not enough image overlap to do a really good model of the topography, which makes sense because there's not. There's only one track of imagery. There's no side lap. So that's to be expected. Before I move on, I'm actually going to resize my bounding box, and if you come up to the top and hit this drop down, you can say resize region. And the reason I want to do this is I don't want to process any more data than I have to, and also the town is really only on this left side, so I'm just going to remove all that stuff on the right to sort of save some space later on. So we're good there. I can click on my mouse again. You might also want to rotate it up and make it really flat, and then try to resize the box here as well to just reduce, especially if you're having water noise, this can help reduce its modeling of all the annoying water. So happy with that, we will move on. So again, these images don't have any coordinates. We're not in a coordinate system, and so we can't actually build a DEM at this point. But what we can do is we can build a mesh. So right now these are all floating points, and if you were to zoom way in, you would see they are individual points. And so what the mesh does is it's going to just connect them all together using triangulation. And since we're just trying to do this quickly, get it all over with, we're not going to do the most accurate mesh. And also your computer might not have enough memory for it. Like if you put it on high, that's just too many faces. Your computer's not gonna make it. So I'm actually gonna run it on low and use this height field of 2.5D. So 3D would retain all surfaces in 3 dimensions, so the floating points would be all connected together, and any like overhangs or anything like that would be retained. 2.5D is like it's like a DEM, where at each XY point the highest value is considered the height, and that's it. So that'll save us some space, so we're just going to run that and press OK. You can look at advanced, and interpolation should be the default, so leave that there. You could do vertex colors, but we're not going to. So it connected all those points together, and you can see now there's some obvious noise in the rivers and around the buildings, kind of look like strange tents, but overall it worked really well, and it was fast, it was easy, and it gives a really good idea of what the place looks like. So this will help, because remember, orthorectifying, the whole point is like things on hillsides and stuff. If you just looked at one image, they might look further or closer to like this riverbank, for example, than they actually are. So the ortho is going to fix that in our top-down image, and the way it does that is by modeling this hillside. So even though it's a little chunky and strange looking, it's still a hillside. It's got the steepness probably about right, so it should be better than just looking at a raw image. So we will save and now build our ortho, and the projection will be top XY, planar. You should be able to leave everything alone. The surface is mesh and will blend with the mosaic. Definitely enable hole filling, and you could refine seam lines. I'm not going to, it just takes more time. Notice that the pixel size is ridiculously small, again because it's not projected. It doesn't know how big this image actually is. So just leave everything as default and press OK. So I've got mine made. I'm going to go to Workspace and double click Ortho Mosaic, and it takes me to this Ortho tab, and here I can see it. So the actual images are orthorectified and displayed here, all stitched together in a mosaic, and I had done the bounding box to this stream here, so that's where it ended, and the flight only went so far as the other side of Airport Road, so that's as far as we got. But you can see it worked out pretty well. You can zoom in on buildings and it's as if we're looking straight down on them, which is good. And down on some cars, the resolution is also really good. I can come and look at this tank farm. And tanks and things and even buildings, they tend to get wobbly just in general. And these ones aren't even orthorectified because there wasn't enough images to really do it very well. So you got to be kind of mindful of that and know that it's not going to come out perfect. It's going to look kind of weird. So, but it's still a really high resolution, stitched together image, and it's exactly what I was expecting. Basically, it tells me a lot of information. There's a lot of strange artifacts, and there's nothing we can really do because that's just the way that this image was collected. It just wasn't collected in a way that would help remove those artifacts. But it still looks really good. Lots of good stuff. I'm really happy with it. And so now I will right click and export orthomosaic as JPEG/TIFF/PNG. Gives me more options. Coordinate system remains as a local coordinate system, and the pixel size here is fairly small, of course. Background color is black. So basically all this stuff should be default and you can leave it alone. We'll do TIFF compression of LZW, and that'll make any no datas not take up any space. And then don't have any of these checked on because Agisoft will, or Esri ArcGIS will take care of some of these things for us. And then when you press export, you can actually save the file. So I'm going to go to my rasters folder, and I have one saved here already. I decided to give the location name first, and then year, month, day, so I know the exact day it was collected. And then I just type ORT to say it's an ortho, black and white ortho, and press save. So that's pretty much it for the Agisoft side. To actually get this georeferenced, all you have to do in ARC is just bring it in and it'll bring it in without a coordinate system, so you could either georeference it first or define the projection first, but when you georeference, essentially just find something that looks similar to today, like maybe just this tank farm location, and then just georeference it to that spot, and then pick something else like a lake over here, and georeference it just roughly at first, and then fine tune it later and delete your initial rough points, and that'll give you a really good georeference product. I wouldn't go overboard, because the more georeference ties you add, the more it can actually warp and skew the image, which should be pretty orthorectified. But keep in mind, since we didn't have that overlap, especially around the edges, those areas probably won't be very well ortho. So I wouldn't use probably like 60 or 70% from the edge of the image. If I can use a selection to kind of say, I'd probably only focus on like this part of the image to actually do my georeferencing, and anything outside of that I just wouldn't trust to do that, and that should save you some pain. And then once it's georeferenced, you can use the tool define projection, and what that'll do is you can tell the program what projection this image is in, and then it won't move around. It'll be all happy. You'll have a perfect ortho from 1975. Alright, thanks, and I hope that works out for you and you don't run into any issues like I did. Wonderful.